Hello all, I'm filming this video on June 17th, 2026. So the exams are over for both the Edexcel exams that are taken in England and the international exams that are taken all over the world. But I decided to film this video because one of the main problems that this channel is facing is that if I keep uploading just past papers, the channel is going to go through inactivity during summer seasons or during seasons when people are not really studying or taking exams or stuff like that. So I want to upload this video to see how many people are going to watch it. So that's the first reason. And the second reason is that this paper, paper 1, Core Physics 1, as it's called, it's at the advanced subsidiary level, and it's taken in England, is my understanding, okay? This paper from 2025, okay, the most recent one, has the fastest growing viewership in my channel. I don't know why that is. So I decided to, this is also another experiment. So since people are watching this so much, I figured that I can upload one more. So this one is from 2024. Okay, so we're gonna get to it and see how it goes. Oh, my suspicion is that the large viewership comes from students who are now finishing their GCSE level exams, and they want to see or to gauge whether they are interested in physics, so they continue taking it at a higher level, or these are students preparing to take some sort of an exam. I don't know. Let me know why you're watching it and where you're watching from. I'm interested in this kind of statistics because I'm trying to figure out still where I want to go with this channel. And I'm also very excited for something that, okay, it's not at the high school level. I went over a past, not the past paper, sorry. I went over a research paper that is of interest to me, and I created a small software package that actually goes through the calculations shown in the paper or something like that. So that's the other direction I want to give this channel, like discuss actual cutting edge research in physics that's going on right now. But anyway, let's go with the paper and see how it goes. So, okay, question 1: which of the following quantities is a scalar quantity? And the first option is energy, which happens to be a scalar quantity. Okay, so that's the correct answer. And you can immediately figure that the moment of a force, momentum, and velocity, all those are vector quantities because they come with a direction, right? Whereas energy doesn't have a direction. Okay, so question 2: two ice skaters, P and Q, are close together and stationary on an ice ring. P pushes Q and they move away from each other. The mass of P is greater than the mass of Q. So let's write that down. So mass of P is larger than mass of Q. Okay. Assume the frictional force between the ice and the skates is negligible. Which of the following statements is correct? So before we read the statements, let's make a model. Okay. So this is the ice skate ring. Okay. And this is again the ice skate ring. And let's model the two skaters as boxes, okay? So this is skater P and this is skater Q, okay? So their momentum, the initial momentum is 0, right? Before they push each other, okay? And again, the mass of P is larger than the mass of Q. And after they push each other, okay, what's gonna happen? P is gonna move to the left, okay? And Q, so that's P and that's Q, and Q is going to move to the right, okay? Their momentum should stay 0, right? Because momentum, linear momentum, is conserved, okay? So we can write that the mass of P times V of P is equal to the mass of Q times VQ, all right? So I'm going to come up here. So we can see immediately that the velocity of P is equal to the mass of Q over mass of P times VQ. So Vp is larger than Vq, okay? And this is because this ratio is smaller than 1, because the mass of Q is less than the mass of P. Okay, so Mq over Mp is lesser than 1. Okay, let's write it like that. Okay, so let's read the options now. So option A, P and Q move at the same speed. That's impossible. Momentum wouldn't be conserved. Option B, P and Q have the same magnitude of momentum. That's actually true, right? So the magnitude of momentum for P is mp equals to times Vp, and this is equal to mq times Vq. So that's actually correct. But let's read the other options as well. P has a greater magnitude of momentum than Q. That's option C, which is wrong because that will violate the principle of conservation of momentum. D, P moves faster than Q. Again, we showed that that's not the case. So B is the correct answer. Let's move on. Option 3, a ball is thrown and follows the path shown. Air resistance is negligible. Which of the following is a free body diagram for the ball at position X? Okay, so what kind of forces does X experience? It experiences its weight, right? Which is, its weight, which is a force that always points down, and air resistance is negligible. Okay, so there are no other forces really. So the actual answer is A. Okay, so they want to throw you off with option B and options C, because that arrow there is actually the velocity. Okay, because the velocity is tangent to the motion, to the trajectory, as it's called. So options B and C are totally wrong. Then D kind of makes sense if you have air resistance, but then air resistance will be, yeah, I mean, air resistance will be in that direction. If you had air resistance, D would be correct, but yeah, that's wrong. So A is the correct answer. Let's move on. The circuit shown contains a cell with internal resistance. Okay. The cell is replaced with another cell with the same EMF, electromotive force, but greater internal resistance. Which of the table shows what happens to the ammeter reading and voltmeter reading? Okay, so this battery over here has an let's call it epsilon, and an internal resistance, let's call it lowercase r. Okay, so let's assume that there is a current in this circuit. Okay, I mean, it's not an assumption. There is a current, sorry. Okay, the way I put it, it was wrong. So the current flows in that direction. And let's assume that this guy, the large resistor, has a resistance of capital. Then we have that, let me go down here, okay? E minus the current times the internal resistance minus I times this, the resistance of the resistor is 0, right? So we can solve for R. So we have I is equal to the EMF over the internal resistance plus R, right? And this is what the ammeter is going to show, that current, okay? Now for the voltmeter is across the resistor R, okay? So that's going to show the voltage across that resistor. What is that voltage? The voltage is going to be equal to the current times the resistance of the resistor, right? But I, we just calculated I to be E times R over R plus R, okay? Now they tell us that the cell is replaced with another cell with the same EMF, but greater internal resistance. So what's going to happen? So if the internal resistance increases, then I decreases, right? Because R is in the denominator of the current, okay? Same happens with the voltage across the voltmeter, okay? By the way, I forgot to write, so that's what the voltmeter will show, okay? So the voltage will also drop because the internal resistance is in the denominator. So both decrease, and the correct answer is D. Okay, so it takes some analysis here. Oh, by the way, I forgot to say the thing that I always say in past papers. For the multiple choice questions that award 1 mark, you should spend about a minute. Okay, in this case, we spend probably 2 minutes. It's fine. Some of them are harder than some others. So, but try to stay on time. And then in questions that award 10 marks, you should spend about 10 minutes. Okay, and this is because I think there are, you have 90 minutes for 80 marks, something like that. So the rule of thumb is to spend about a minute per mark. And the other thing I always say is that, of course, go through the questions that you know how to respond first, okay? So you build momentum and come back for questions that you didn't know how to solve in the end, okay? So you have more confidence, because if you lose time on problems that you don't know how to deal with, that's gonna waste your time and also make you lose confidence, okay? So yeah. Anyway, let's move on. Okay, question 5. A copper wire has a cross-sectional area A and length L. There is a potential difference V across the wire. The resistance of the wire is capital R. Okay, copper has N conduction electrons per unit volume. Which of the following expressions gives the drift velocity of the electrons along the wire? Okay, so for this one, it's good to actually maybe, I mean, if it helps you, it helps me definitely. It's good to draw a scheme of what's going on. Okay, so this is your wire. Okay, it has a length of L and cross-sectional area A. Okay, and we apply some potential difference V. Okay, so there is a current in this circuit, right? So yes, that's the current. Okay, now that current I is going to be equal to V over R. Let me for a moment write V like that, okay? So that I do that to distinguish from the other V which you will use for velocity, okay? So I is V over R, but what is I for conductors? Is equal to the number of conduction electrons times the charge of those electrons. Actually, the formula in the back of your paper is Q, but Q is equal to E, okay? So N times E times the drift velocity times the cross-sectional area. And this whole thing is going to be equal to V over R, right? So we only have to solve for V. So V, the velocity, the drift velocity for the electrons is equal to V, the potential difference, over N times E times the cross-sectional area times the resistance, okay? So let's go check our options. So this is the correct answer, C. Okay, and the other ones do not work out dimensionally wise. I mean, everything is totally wrong. Okay, so if you plug in units, you will not get a velocity in options A, B, and D. Okay, let's move on to question number 6. A ball rolls along a table of height 0.83 meters. The ball has a horizontal velocity of 1.72 meters per second as it falls off the edge of the table. Which of the following is an expression for the speed of the ball in meters per second as it hits the floor? Okay, so here we have to resolve, not resolve, we have to find the resultant velocity pretty much. Okay, so again, it's good to draw a scheme. So let's assume that this is a table, okay, and we have the ball rolling with some horizontal velocity Vx, x as in the x-axis, okay? So this velocity is constant and equal to 1.72 meters per second, and then it reaches the edge of the table and it drops from the table that has a height of 0.83 meters, right? So it's gonna follow a trajectory like that and drop to the floor. Okay, so as it drops to the floor, so let's say that the floor is here. So Vx is still gonna be a component of the velocity, and the other component is gonna be Vy. And the problem asks to find V. Okay, so V is the square root of Vx squared plus Vy squared from Pythagoras. Okay, now we know what Vx is, but we don't know what Vy is. Okay, so for that we're gonna use Suvat equations. So in the y direction, actually for completeness, excuse me, we can write that Vx is 1.72 meters per second. And then in the y direction, we can use Vy squared is equal to Uy squared, where U is the initial velocity in the y direction, okay, plus 2 times acceleration times the distance traveled, which is h, which is 0.83, okay. The initial velocity in the y direction is 0, right? Because the velocity in the y direction starts growing once the ball falls, right? So Vy squared is 2 times 9.81 times 0.83, okay? And since we need Vy squared, I'm not gonna calculate Vy, but instead we can write immediately that V is the square root of Vx squared, which is 1.72 squared, plus Vy squared, which is 2 times 9.81 times 0.83, which is option C. So another kind of difficult problem for a 1 mark question. I mean, I think it took us some time to figure it out. So anyway, let's move on to question 7. Which of the following units is equivalent to the joule? Okay, so let me think about how I want to do this. Newtons times seconds. Okay, so Newton is a kilogram times meters over second squared times seconds. So that's actually the unit for momentum. So A is wrong. B, kilograms times meters over second squared. That's the Newton actually. So that's wrong. Then watts times seconds. 1 watt is 1 joule per second times seconds. So that's the joule. So that's the correct answer. Okay. And then D, kilograms times meters per second is the same as option A. So that's also wrong. So the correct answer is C. Okay, let's move on. Okay, question 8. A simplified velocity time graph for the flight of a drone is shown. Okay. Which of the following is a displacement time graph for the same flight? Okay, I don't have enough space. So, but anyway, recall that V is dx over dt. So it's actually the gradient of x versus t. Okay, so in this region, the velocity is positive, which means that the gradient is positive, and since v is constant, okay, the x versus t graph is linear. Okay, now let's go see, do we have any graph that is linear? So A and C are candidates, B and D are wrong. Okay, now in the second part of the motion, the velocity is negative. So let me write here. So in the other region, V is less than 0, which means that gradient is less than 0, and x versus t is linear. Okay, so option A works, okay, because we have a positive gradient and then a negative gradient, and the graphs are linear as needed. Okay, C doesn't work because it's some weird sort of motion in which I don't know what's going on there. So anyway, C doesn't work. So A is the correct answer. Let's move on. Question 9. A windsurfer stands on a windsurf board and holds onto the sail as shown. As the force from the wind increases, the windsurfer leans further back. Explain how leaning back further keeps the windsurfer in equilibrium. Your explanation should make reference to moments. Okay, before we work this out, let's try to imagine what kind of forces we have involved here. So there is some wind, okay, so that's the wind with blue, okay, that pushes the sail in this direction, okay. Of course, someone might protest that maybe the wind is blowing in the other direction, but in that case, the surfer will want to lean in the other direction. So this is the correct direction. I hope it makes sense. If it doesn't, ask me in the comments and I will explain further. So let's call that wind force. Okay. So there is a pivot here. Okay. Therefore, that force tends to rotate the sail, the the thing, the windsurf board, whatever. It tends to rotate it anti-clockwise. Now the surfer has a weight, right? And it also, okay, the distance from the pivot is this one for the wind, and for the weight, this is the distance to the pivot, okay? So the surfer creates a moment that is clockwise, that wants to balance what's going on, okay? So if he leans further back, that moment actually increases, right? Because the distance of the center of mass increases, okay? So, yeah, and of course, the weight applies in the center of mass of the surfer. So as he leans back, the center of mass gets more away from the pivot, okay? So let's write all these things down. Okay, so I just tried to show you, excuse me, what's going on. So let's write down that the wind pushes the sail, okay, creating an anti-clockwise moment. Oops, what am I writing? An anti-clockwise moment. Okay, a moment about the pivot. Okay, it's important to write that down actually. So about the pivot, because moments are defined about the point. Okay, so if we don't mention the point, it's pointless. Okay, that kind of rhymed. I didn't do it on purpose. So anyway, the weight of the surfer, okay, acts down. Oops, acts down through the center of mass, So I wrote it like that. Com means center of mass. Okay, and creates a clockwise moment. Okay, a clockwise moment about the same pivot. Okay, now when the surfer leans back, okay, the distance from the pivot, okay, increases, okay, so the clockwise moment increases, okay. The surfer keeps leaning, okay, until the clockwise moment balances the anti-clockwise moment. Okay, and that's it. I mean, that's a good enough answer. Despite coming from an island nation, I never tried windsurfing. I know it's a shame. There are many things that I should try in life that I haven't tried yet, but we'll see. I'm getting older, but that doesn't mean that I'm not interested in things. So this is something I think I would enjoy, and I like running and boxing. So and I used to play football when I was younger for fun. I never played anywhere that you would know. So I just played for fun, and so I'm trying to say I have good balance. So I think I might be able to do it. But let me know if you ever tried wind surfing, guys. So anyway, let's move on to the next question. Okay, question 10. A coin is given a push and moves across a table. Okay, the coin moves 65 centimeters before coming to rest. There is a mean resistive force of 2.2 times 10 to the negative 3 newtons on the coin as it moves. Calculate the initial speed of the coin, and they give us the mass of the coin. So this is a strange problem. I never expected to encounter such a problem. So I mean, now that I go through these A-level tests, it's sometimes it's fun for me. Actually, it's fun. No, what I'm trying to say is that I encounter questions about things that I never encountered before. So it's fun. Anyway, so this is the coin, say, okay. So it slides for 65 centimeters. and it comes to rest, okay? And the idea is that there is a resistive force acting on the coin, okay? So that resistive force provides a deceleration that stops the coin, right? Can we calculate that? We can, because they give us the force. So force is mass times this deceleration that we need, okay? So the deceleration is F over m, okay? It's actually better to write minus F over m, simply because it's a deceleration, so it comes with a negative sign, and also the resistive force F points to the left, so left is considered negative in this case, okay? So this is equal to minus 2.2 times 10 to the negative 3, and that's newtons, and then the mass of the coin is 8.5 times 10 to the negative 3 kilograms, okay? So A is equal to minus 0.26 meters per second squared. And let me show you why newtons per kilograms give you meters per second squared. So newtons per kilograms is equal to kilograms times meters per second squared. And then we are dividing with kilograms, so kilograms cancel. Okay, hope that this makes sense. And then all we have to do is to use Suvat equations. I ran out of space there, so I'm going to use a clean page. So we can use v squared, the final velocity squared, is equal to u squared minus 2 times the deceleration times s. It's actually a plus in the original equation, but here we have deceleration, so we get the minus sign, and also the initial velocity, sorry, the final velocity is 0. Okay, so u squared is 2as, so u is the square root of 2as, or the square root of 2 times 0.26 times 0.65, okay, which is equal to 0.58 meters per second, which you can also write as 0.6 meters per second, and that's the answer, okay. Part B. The coin is pushed again, but with a larger force. The coin moves beyond the edge of the table and falls to the floor through a vertical height of 1.2 meters. The speed of the coin as it reaches the edge of the table is 0.4 meters per second. Calculate the horizontal distance traveled by the coin as it falls to the floor. Okay, this is somewhat of a complicated problem. Let me draw the scheme. I like drawing schemes, by the way. It helps visualize what's going on in physics problems. Okay, so this is a table, and the coin launches with a horizontal velocity, which we call Vx, like in the problem we encountered in the multiple choice section. So Vx is 0.4 meters per second. Okay, the height is 1.2 meters, and we need to find the horizontal distance. Let me try again. And we need to find S, is horizontal distance it traveled. Okay, so we need a few Suvat equations to do that. So the way I went about this, I haven't tried the second way. I should have, but I didn't. So the way I went about it was that, okay, we know the height in the y direction, so we can use, so this part A, so this part B, we can use the height of the table, which is 1.2 meters, is equal to uy times time, right? But the initial velocity in the y direction is 0, simply because it doesn't have an initial velocity in the y direction, okay? The velocity in the y direction starts growing once it falls off the table, okay? Plus 1/2 times the acceleration in the y direction times t squared, okay? So 1.2 meters is equal to 1/2 times 9.81 times t squared, okay? So t squared, so t is actually, sorry, the square root of 2 times 1.2 over 9.81, or 0.49 seconds is the time of flight, which is the same for the horizontal flight as well, okay? By the way, the reason why we don't use minus 9.81 here is because the velocity in the y direction points down, just like the acceleration in the y direction, which is g, points down. Okay, so we found the time, and now we can use the same Suvat equation, but in the y direction. So s is equal to the initial velocity in the x direction times time, plus 1/2 times the acceleration in the x direction times t squared. But of course, there is no acceleration in the x direction, so that term is 0. Okay, so s is 0.4 times 0.49 seconds, or 0.2 meters. Okay, so that's our answer. Okay, this was a somewhat difficult problem, I would say, for 6 marks, because you have to apply equations twice, and you need to think about it a little bit. So yeah, anyway, let's move on. Okay, question 11 gave me some trouble because I never saw a toy like this, and I was a little bit confused about how it works in the beginning until I figured it out. So the picture shows a toy car. There is an inflated balloon attached to the car. As the balloon deflates, air is released from the back of the car, and the car starts to move. Okay. Explain, with reference to Newton's laws of motion, how the release of the air from the back of the car causes the car to start to move. So the way it works is that there is air in this balloon that gets released through a tube that is in the car, I guess. And the air is released from the back of the car. So air is moving to the left, so the car moves to the right. So that's Newton's third law. But let's write it down properly. So the balloon, the balloon exerts a force on the air inside it, pushing air out through the back. Okay. By Newton's third law, the air exerts a force, okay, of equal, let me write it. So by Newton's third law, the air exerts an equal and opposite force, okay, back on the balloon, okay, and by extension to the car, okay, and this force is directed forward. Okay, we need more space. So this reaction force, okay, is a net resultant force on the car, okay, and by Newton's second law, which tells us that the resultant force is equal to mass times acceleration, the force causes the car to accelerate, okay, from rest and start moving forward. So yeah, this is the story of how this toy works. I have to admit that as a kid I was a little bit of a snob, so I only like toys that I perceived as well done, well made, well thought out. So something like that wouldn't impress me as a kid because it's cheap, like a balloon deflating and making it move. I was excited by, I don't know, I really liked Legos, and especially the ones that had moving parts and small engines, and or I really liked RC cars and stuff like that. I never liked toys that I perceived as cheap. So this one, I think I would perceive it as cheap, and I wouldn't like it. And I was a very selective kid, so I wouldn't accept a toy that I didn't like. I wouldn't play with it. I would just give it away to someone else. So anyway, small history of someone who ended up being a physicist. So anyway, let's move on. Question 12. A student carried out an experiment to determine the resistivity of a metal alloy. The student used a wire made of the alloy and connected it in a circuit as shown. Okay. Describe how the student could have measured the diameter of the wire accurately. So, okay, you can use a micrometer screw gauge, okay, which has a better resolution than a ruler, okay, and you can take multiple readings you should take multiple readings. So take multiple readings at different points, okay, along the wire, okay, and at different orientations at each point, and average, okay. Average means take the mean, and actually maybe write it like that, and take the mean. Okay, this is what I mean. Oops, take the mean. And what do we mean by multiple orientations is that, okay, if this is the wire, okay, and you need to measure the diameter. Okay, first take measurements at various points along the wire, okay? And then when we say multiple orientations, if this is the cross section, you should measure the diameter along this orientation, and then along this orientation, and maybe along this orientation. Take as many as you need, and then take the average. Okay, let's move on. Okay, part B, the student made the following measurements. The voltmeter reading was 1.96 volts, the ammeter was 0.57 amps, the diameter of the wire, he measured the length, or she measured the length of the wire. Okay, calculate the resistivity of the metal alloy. Okay, let's first calculate the resistance. So using Ohm's law, so V over I 1.96 over 0.57 yields 3.44 ohms. And then we know that the resistance is equal to the resistivity times the length of the wire over the cross-sectional area. So rho is the cross-sectional area times the resistance over L. So the resistance is 3.44. And then the diameter is pi. Sorry, the cross-sectional area is pi times the diameter squared, so 0.58 times 10 to the negative 3 squared, and then we need to divide by 4, and then we need to also divide by the length, which is 0.835. Okay, and this gives the resistivity as 109 times 10 to the negative 6 ohms times meters, which is about 1.1 times 10 to the negative 6 ohm times meters. Okay, let's continue with part C. The student stated that the ammeter reading was the most significant source of uncertainty in the calculated value of resistivity. The percentage uncertainty in the ammeter reading was 0.9%. The percentage uncertainty in the measurement of diameter was 0.8%. The percentage uncertainty in the measurement of the length was 0.1%. And in the voltmeter reading was 0.3%. Assess the validity of the student's statement. So before we do that, we need to write down that the resistivity is equal to the cross-sectional area over L times the resistance. And the cross-sectional area is equal to pi d squared over 4. And then we have L in the denominator, and we also have voltage over I from the resistance, right? So to find the percentage uncertainty, when we are multiplying or dividing quantities, we sum their percentage uncertainties and we ignore the constants, okay? And I have a video, by the way, on this in my channel. Go search and find it. Maybe I will link it in the description of this video, but if I don't, just search for it and you will find it. So the percentage uncertainty in the resistivity is equal to the percentage uncertainty in the voltage in the voltmeter plus the percentage uncertainty in the ammeter reading plus the percentage uncertainty in L plus the percentage uncertainty in D squared. But when we have percentage uncertainties of quantities that are some sort of a power, then this is actually equal to 2 times the percentage uncertainty in D itself. Okay, and if we go inspect, we will see that the percentage uncertainty in the measurement of diameter is 0.8%. So 2 times 0.8% is 1.6%. Okay, so we can write that, let me find black, okay? So the percentage uncertainty in D squared is equal to 1.6%, and it's larger than the percentage of uncertainty in the the ammeter reading in I, which is equal to 0.9%. Okay, so the student is actually wrong. Okay, and that's our answer for part C. Okay, so let's move on to question 13. The diagram shows a car being driven down a slope at a constant speed. Complete the free body diagram for the car. Okay, this is a little bit tricky because, okay, we will have the weight as usual, which points down. Okay, and we need the reaction from the floor. Okay, something like that. That's the reaction, which is of course perpendicular to the floor. So if we use the car, so that's going to be the reaction, that's going to be the weight. And are we done? We are not done, because we also have frictional force. How do we know that? Because the car is being driven down the slope. If there was no friction, it would just slide. Okay, I mean the wheels wouldn't even turn. Okay, so you need to know your everyday life to answer that part, I guess. So we have a frictional force which is opposite to the driving force. Okay, so that's the free body diagram. Okay, I don't like R because, okay, it's perpendicular to the incline. Okay, I hope it makes sense. So let's move on to part 2. Oh, I forgot to draw there. Okay, that's the frictional force. And okay, there's a driving force. Okay, driving force is from the engine. Okay, in case you got confused about it. So the total resistive force acting on the car is 2,530 newtons. By the way, they tell us that there is a resistive force anyway in part 2. That's another thing about the A levels. Sometimes if you're confused about part A, part B might actually tell you what it wouldn't tell you the answer, but it will guide you towards the answer. So yes, there is a resistive force. Okay, calculate the driving force required for the car to maintain a constant speed. Okay, constant speed, V equals to constant, means that the sum of all forces in the driving direction is 0. Okay, so how many forces do we have in that direction? Actually, let me erase and make a better diagram here where the car is. Okay, so we have the weight that points down. We have the reaction from the floor. Okay, let's call it N, and we have the frictional force F, and we have the driving force D. But we also need to analyze the weight. Okay, so don't forget that. So we have two components for the weight. If this angle is 11, then this angle is 11. Okay, everything is cramped there. I don't like it, but okay, so that angle is 11 degrees. How do we know that? Because this side is perpendicular to this side, and then this side, this vector, whatever, is perpendicular to this side. So the inscribed angles are the same. I hope that makes sense. If it doesn't, ask me in the comments and I will try to provide a better explanation. So, okay, so we have a component for the weight times cosine 11 that cancels the reaction from the floor. But we also have another component, which I'm going to draw it there, weight times sine of 11 degrees in the same direction as D. Okay, so to have a sum of all forces equal to 0, we need D plus the weight times sine of 11 degrees to be equal to the frictional force F. Okay, and yeah, is there anything else to say? That component is equal to comes with a sign, because the way I remember things up to this date, okay, like 55 years after I started studying physics, it hasn't been that long, but I'm exaggerating as usual. So for example, this component touches the 11 degree angle, so that's a cosine. The other component this component doesn't touch the 11-degree angle, so it's a sine. Okay, that's how I remember it. Okay, so we need to search for D. So D is F minus weight times sine of 11 degrees. So we have 2530 minus 1.2 times 10 to the 4 times sine of 11 degrees. And this yields 240.3 newtons for the driving force. Okay, let's move on. Part B. A very steep road may have a lane to the side filled with deep gravel. Actually, I live in an area of the island that has really steep roads, as described. So near my house, there are actually 2 such lanes with gravel. Nobody ever used them. I mean, I don't remember any occasion where a car, I don't know, the brakes were faulty or something like that, and they needed to use that. Because as you go down a steep road, if your brakes break, okay, you're done. I mean, it's too steep. You have to come here and see it. So anyway, a very steep road may have a lane to the side filled with deep gravel. A vehicle with brake failure can drive onto the lane and will be brought to rest as the vehicle's wheels sink into the gravel. The graph shows the decrease in velocity of a van as it comes to rest in the gravel. Okay. Question I. Calculate the maximum decelerating force on the van, and they give you the mass of the van. Okay, we have to find. Okay, since we have a velocity versus time graph, then the gradient is delta v over delta t, which is equal to the acceleration. Okay, this is not a linear graph, so we have to find sort of like the steepest gradient, which is going to be the maximum possible deceleration, because they ask, the question asks for the maximum decelerating force. So the maximum deceleration, from what I figured, you might have a better guess, but I used, what did I use? This part of the graph. I think the steepest is here. Okay. So the tangent at any point on this graph is actually the deceleration. Okay. So I figured that the steepest point is this point over here. So I actually used, what did I use? This part, starting from there down here. You can see that that part is sort of linear, so I took it as such. So okay, that's 3 seconds. Okay, and that's 2 seconds. Okay, so delta t is actually minus 1 seconds. Okay, because you go from 2 to 3, and then in this direction, delta v is equal to 12.5 minus 5.2, because I figured that what did I figure? Let me think. So that's 5.2. Okay, so the acceleration is minus 7.3 meters per second squared. So the maximum decelerating force is mass times this deceleration. So 2,400 kilograms times minus 7.3 meters per second squared. So that's 17,520 newtons is the answer I found. Okay. Your answer might differ because you might have used a different starting point and so on. So is this good enough? I think so. So let's move on to part 2. Describe the energy transfers taking place as a vehicle comes to rest in the gravel. So as the vehicle slows down, okay, kinetic energy is from the van. Okay, it's important to write that. So kinetic energy from the van is transferred to kinetic energy on the gravel. okay, on the gravel particles displaced, right? And also thermal energy generated by friction with the tires. I hope this makes sense. Let's move on to the next question. Okay, question 14. A light emitting diode, LED, is placed in a circuit with a fixed resistor and a variable power supply. An ammeter and a high resistance voltmeter are also connected as shown. The graph shows how the current I through the LED varies with the potential difference VLED across the LED, and we see that there is a minimum voltage at which the LED is not operating, so below 0.4 volts. Okay, question A, when the potential difference across the variable power supply is 6 volts, the ammeter reading is 12.5 milliamps. Calculate the resistance of the fixed resistor. Okay, so first of all, we will have VR plus VLED. That must be equal to 6 volts. So we need to find the voltage across the LED. So the current across the LED is 12.5 milliamps, which is that point over there. So we can see that that's 12.5 milliamps. And in the x direction, every little square is equal to 0.02 volts. You can check for yourselves. So that point over there is 0.7 volts. And the point we are interested in is 2 deviations past that. So 0.74 volts is the value of the voltage across the LED. So we can come here and find VR is equal to 6 minus 0.74 or 5.26 volts. Okay, and now that we have VR, we can find the resistance. So the resistance is VR over I. Since the LED is connected in series with the resistor, the same current passes through both. So 5.26 over 12.5 times 10 to the negative 3 yields 420.8 ohms as the value of the resistance. Okay. B. The ammeter and voltmeter were removed from the circuit. The variable power supply was replaced by a signal generator and an oscilloscope as shown. The output from the signal generator is shown on the oscilloscope screen below. The output varies between 6 volts and minus 6 volts. Points A, B, and C represents instants of time. Explain why the LED flashes. Your answer should refer to the output between times A and C. So first of all, before we write anything down, notice that in this part, okay, the voltage is plus 6 volts, okay, and at plus 6 volts, as we saw earlier, there is current in the variable in the LED, okay, and then it becomes minus 6 volts, okay. So at minus 6 volts, if we come to the graph, we see that we need at least 0.4 volts. So there is no current in the LED, okay, and then the voltage switches back to plus 6, so the LED is on. So we have on, off, and on. So this is what's going on. Okay, so let's write this down. So from A to B, and we have the following. So the potential difference across the circuit is positive, okay, meaning the LED is forward biased, okay. This positive potential difference, okay, drives a current of 12.5 milliamps through the LED, okay, as shown in the IV curve, okay. Now current flows in the LED, so LED is on, okay. From B to C, the voltage is minus 6 volts, okay. So PD is negative, so the LED is reverse biased, okay. Diodes only allow current to flow in one direction, okay. So no current, okay. So no current means no light, okay. And Flashing on and off is due to the generator alternating between plus and minus 6 volts. Okay, so this is enough, I think. So by the way, this is a long writing problem as denoted by the asterisk, okay? And in these types of questions, try to describe the situation as thoroughly as possible. And since 6 marks are awarded, you should have in your mind that you should provide about 5 to 7 talking points, sentences, something like that. Okay, this was question 14. Let's move on to question 15. Okay, question 15. Electric cars are powered by a large battery within the car. Okay. Question A. The manufacturer of an electric car states that the battery stores a maximum charge of 110 amps times hours. The graph shows how the current through the battery varies with time as the battery is charged. Okay. The manufacturer claims that it takes 5 hours to reach 90% of the maximum charge. Criticize this statement. Okay, first of all, current is charge per time. So charge is current times time. Okay, so area under I versus T curve, is charge. Okay, I hope this makes sense. So at 5 hours, this is the mark, okay, the 5-hour mark. So we need to calculate this area. Okay, so let me show you what I did. I divided it into this triangle. So this is a right triangle. Okay, this is another right triangle. Okay, so let's call this maybe 1, 2, and then we have a rectangle, 3. Okay, so Q is the area under this curve. So, okay, we have, first of all, 5 minus 0.5. This is the area of the rectangle, okay, times the height, which is 17.5. So this is 3, okay? Then plus 1/2 times 2.5 times 5 minus 0.5. Let me see which triangle is that. This is this triangle 2. Okay, sorry about that. Plus 1/2 times 0.5 times 17.5. This is the area of triangle 1. Okay, and this is equal to 88.75 amps times hours, sorry, which is about 89 amps times hours. So let's use a clean page. So full charge comes at 110 amps times hours. So 90% of that is 0.9 times 110, which is 99 amps times hours, which is larger than 89 amps times hours, which we calculated. So statement is wrong. Okay, let's move on. B, the manufacturer tested the car by driving it at constant speed along a horizontal track. The manufacturer determined that the maximum range of the car was 160 kilometers, showed that the average value of the resistive forces of the car was about 800 newtons. The efficiency of the car is 85%, and the energy stored when battery has maximum charge is 42,000 watts times hour. Okay, so first of all, let's convert this kilowatt hours into joules. Okay, so that's 1000 watts, which is joules per second, times 1 hour has 60 minutes times 60 seconds. Okay, so that factor right there is 3.6 times 10 to the 6 joules. Okay, so the energy of the provided by the car is equal to the efficiency, actually the useful energy, okay, to follow the Mark scheme. So the useful energy is equal to the efficiency times the energy stored, okay. So we have 0.85 times 42 kilowatt hours, and then 1 kilowatt hour is 3.6 times 10 to the 6 joules. So the useful energy is 1.29 times 10 to the 8 joules. Okay, now the work done by the resistive force is equal to the resistive force times the distance, right? But the work done is equal to the energy useful, okay, which is equal to F times D. So F is E times D, E useful, okay. So 1.29 times 10 to the 8 over 160,000 meters, which is 160 kilometers. And joules can be written as newtons times meters over meters. So we get 806.25 newtons, which is very close to 800 newtons that we were asked to prove. Okay, now there is a part 2 in this question. Okay, part 2, the manufacturer repeated the test on a sloping track as shown. This reduced the maximum range of the car. At the new maximum range, the car had moved upwards through a vertical height of 3 kilometers. Calculate the reduction in the maximum range of the car, and we are given the mass of the car. So, okay, we need to think about this. First of all, let's calculate the GP. So let's assume that's the 3 kilometers height. So the GPE at 3 kilometers is equal to the weight, the mass times, okay, I went a little bit fast, so I'm trying to say this is equal to mgh. So 1300 kilograms times 9.81 times 3000 meters. The units are kilograms, meters per second squared times meters, which make joules. So GP is 3.83 times 10 to the 7 joules. Okay, so now what changes from before, and I'm going to go to the back of the paper in the clean page that we used earlier. So this is part 2, this is part 1. Okay, and we continue here. So the useful energy from before will now be used to overcome the gravitational potential energy plus the resistive forces, the work done by the resistive forces. And that work done is going to be equal to the resistive forces times S, where S is the new range, so that's S, and the resistive force is equal to, it's in the same direction as, is in the same line as the displacement S, okay? So I hope this makes sense. Okay, so now we have S is E useful minus the GP over F, the resistive force. Okay, now the useful energy is 1.29 times 10 to the 8 minus the GP, 3.83 times 10 to the 7 over 806.25. So this is equal to 112.5 kilometers. So I will need another clean page. So the reduction is equal to 160 minus 112.5, which is the new range. So the reduction is 47.5 kilometers. Okay, this was question 15. Let's move on to question 16. Okay, so this is an experimental question. So for those of you who take the international test, paper 1 from England is sort of like the combination of unit 1 and unit 3, okay? So unit 1 is mechanics in general, and unit 3 is the experimental part. So anyway, let's read the experimental question. A spring was hung from a clamp as shown. and we see the meter rule and the spring. A student used the meter rule to measure the unstretched length of the spring. Describe how the student could make this measurement as accurate as possible. So align the zero of the meter rule, okay, with the top of the spring, okay, before reading, I guess, and also position the ruler as close to the spring as possible, okay, and parallel to it, okay. Then view the scale at eye level, okay, to avoid parallax error, okay, and you can also use a set square, okay, so you can more accurately figure things out. Okay. B. The student used the spring to investigate the forces on a uniform rod. One end of the rod was attached to a pivot and the other end was supported by the spring. The distance between the pivot and the spring stayed constant. Okay. A weight was attached to the rod at a distance d from the pivot. As shown, the stretched length of the spring was L. The student changed the position of the weight to vary d, okay, and measured corresponding values of L. The results are recorded below. Okay, so what's going on here is the weight provides a clockwise moment, whereas the spring provides an anti-clockwise moment up. Okay. So question I asks, plot a graph of the extension delta L of the spring on the y-axis against D on the x-axis on the grid opposite. Use the additional column of the table for your processed data. Okay, and we are given the unstretched length of the spring as 3.5 centimeters, which I will call L naught. So delta L is L minus L naught is the column we will need, and it's in centimeters. Okay, so the first measurement is 3.1, the second one is 4.9, and okay, so these are all the measurements, and we have to plot delta L versus D. So we see that D increases nicely by increments of 10, so this is what we will use for our ticks, whereas delta L goes from about 3 centimeters to about 15 centimeters. So we will use ticks of 3. Okay, so you will see. So this is going to be our delta L. So delta L in centimeters, and this is going to be D in the horizontal. So D also in centimeters. So this is the 0. So we have 10, 20, 30, 40, 50, and 60. So every large box corresponds to 10 centimeters. Okay, so this will be 5 centimeters, for example. So every little square is 1 centimeter. Okay, I hope this makes sense. And this is the x-axis. Now for the y-axis, let me think. We can do increments of 2. I think we have enough space. So we can start with 2. So our axis starts from 0. Okay, so 2, 4, 6, 8, 10, 12, 14, and 16. Okay, so that's 1, and then every little box in the y direction is 0.2. Okay, so 0.2 centimeters. Okay, so let me show you the first pair of points, and then I will speed up the video. So the first pair, we have 3.1 centimeters for delta L and 10 centimeters for D. So 3.1 will be that point over there. Okay, and now we'll speed up things. Okay, so these are all the data points, and we can draw a line of best fit. So it will look like, okay, something like this. Okay, we can make it pass through. I don't know why it does that. Okay, let me try again. So, okay, that's my line of best fit. Something's wrong. I don't know why. Okay, let me try something else. So let's bring on the ruler. Okay, so we see we can pass a line that through all the points. So That one looks good. I'm sorry about that. So something like this looks good. Okay, so okay, I could have done better, but something's wrong with my iPad. So forgive me for that. I guess there is a better best fit line that you can pass through all the points, but okay, we will live with that. So okay, so we're done with part one, right? And then we need part two. Okay. Okay, in part two, the student was given the following relationship. Delta L is equal to W, which is weight, times D over K over D capital plus C, where C is a constant, and you can see that actually our graph has a y-intercept, okay? D is the distance from the pivot to the spring, which is 0.875 meters, and W is the weight of the rod, which is 5 newtons. Determine the spring constant K using data from the graph. Okay, so this line has the form y equals mx plus c, okay, where x is d, okay, and y is delta L, and c is the constant. Okay, so the gradient of this plot will be weight over k times capital D, excuse me. Okay, so k is equal to the weight over the gradient times capital D, okay, and the gradient is the change in delta L over the change in D, and I usually just use the extreme values. So when I do things, when I calculate gradients, I use the two extreme points from the data, so this point and this point. To use them, they have to, your best fit line has to pass through them, okay? I do it because it's speedy, and also because a former student of mine figured out that if you use those extreme points, you get as close to the mark scheme results as possible, okay? But okay, it is necessary that your best fit line passes through these two extreme points, okay? But any 2 points on this graph will do, okay? So, but here we will use those two extreme points. So we have 13.8 minus 3.1 over 60 minus 10. So this yields 0.214. And this is a unitless and dimensionless gradient, okay? And the reason is that we are dividing centimeters with centimeters, okay? So that's a pure number I'm trying to say. Okay, so K is 5 newtons for the weight over 0.214 times 0.875, which is meters, okay? So the spring constant is 26.7 newtons per meter, and that's the answer. Okay, this was a funny question, I have to say. So a washing line is attached to two posts which are a distance 5.94 meters apart. A wet blanket of width 2.2 meters is hung from the center of the washing line. The washing line stretches to a length of 6.06 meters and hangs at an angle theta as shown, okay? Calculate the tension in the washing line, and they give you the mass of the wet blanket. Before we do that, there is some geometry that we need to take care of. So first of all, we need to find that angle theta. Okay, so to do that, we're given that this distance is 5.94 meters. Okay, so we can draw a line perpendicular. Oops. Okay, I will need to use the ruler. Okay, I hate using the ruler, but what can you do? So, okay, that's the line I wanted. Let's get the ruler away. Oops. There you go. Okay, now let's call this distance, let's call it x. Okay, now notice that 2 times x plus 2.2 meters is equal to 5.94 meters, right? From the geometry. So this is also x, right? This horizontal distance there is also x, okay? Okay, so in other words, we have x is 5.94 minus 2.2 over 2, or 1.87 meters. Now let's do the same for the hypotenuse of this right triangle, because this is a right triangle, don't forget that. Okay, so we have, if we call this y, we have 2 times y plus 2.2 meters is equal to 6.06. How do we know that? Because this is also y, and the length of the blanket is constant, and we are told that the stretched length is 6.06. Okay, so similarly we find that y is 6.06 minus 2.2 over 2, or 1.93 meters. Now the angle theta is this angle. Okay, so that's theta, that's also theta, of course. Okay, so sine theta is 1.87 over 1.93, so it's the opposite side over the hypotenuse, right? So we find that theta is 75.7 degrees, which makes sense because that looks like a large angle anyway. Okay, so we're done with the geometry, and now we need to work with the forces. What kind of forces do we have here? We have the mass of the blanket at the center of mass, sorry, the weight of the blanket, excuse me. So let's actually call it m times g, because they give us the mass of the blanket. And then we will have the tension, which will apply twice, right? And it's going to be along the wire, along these two wires, along the y side, I'm trying to say. Okay, so okay, so this angle, so this force can be analyzed into two horizontal components that cancel each other and two vertical components. And now notice that how will I convince you now that this angle is actually theta? Okay, and it's theta because you can imagine it as something like this. So you have this situation, so it's Thales principle pretty much. Okay, so if this angle is theta, this angle is also theta, and that angle is that angle over there. Okay, I hope it makes sense. So we have 2 times the tension times, oops, cos theta, not sine, excuse me. Okay, so the horizontal components cancel, so we don't care about them. And in the vertical direction, we have, let me use a clean page. So we have 2 times t times cosine of theta is equal to m times g. Okay, so t is m times g over 2 times cosine of theta, or 9.36 times 9.81 over 2 times the cosine of 75.7 degrees, or 185.6 newtons, which is the answer. Okay, a little bit involved, but it made sense. Okay, so let's move on to part B, the last question in this test. Okay, explain what happens to the height of the blanket from the ground as the blanket dries. Your answer should make reference to the Young modulus of the material of the line. So first of all, let's write down that as the blanket dries, okay, water is lost through evaporation, excuse me. So the mass and weight decreases. So the mass and weight decreases. Okay. Now the tension is proportional to m times g. So if mass decreases, tension also decreases. Okay, but the tension of the line. Okay, but the stress is equal to F times the cross-sectional area. Okay, so if tension decreases, stress also decreases. Okay, because this F is of course going to be T. Okay, it's the is that's the force that extends this line. Okay, so now the Young's modulus is constant. Okay, I mean it doesn't change because the material didn't change. Okay, and and the Young's modulus is equal to the stress over strain, right? Okay, so since stress decreases and E is constant, right, then E also decreases, okay? But the strain, epsilon, is delta L over L. So if strain decreases, delta L decreases, okay? So let me use a clean page. So the line becomes shorter, okay? So shorter from the initial 6.06 meters, okay? So the lowest part of the blanket rises, okay? So the height of the blanket above the ground increases. And that's the answer. Okay, so this was Core Physics 1, which is paper 1 from England, Edexcel AS level, okay, from June 2024. By the way, my understanding is that in England, these tests are only taken once every May, June, okay? So let me know if I'm right about that. If I'm wrong, also let me know. Because the international tests are taken every May, November, and January, from what I figured with these past papers walkthroughs. Please consider supporting the channel if you find what I do important. Also, please subscribe. It doesn't cost anything. I have a buy me a coffee now, and recently I received the first one, which made me really happy. I mean, it was a very small gesture, but I loved it. So thank you to the person who supported the channel. It was the first. This is the first supporter of the channel, so I'm really grateful for that, and I looking forward to more supporters and to see this channel growing. And again, as I said in the beginning of the video, I plan to also start working on more advanced physics concepts because, okay, I have a PhD, so I might as well share the things that interest me and things that I'm passionate about. I mean, I like solving problems and so on. So anyway, I'm not going to say good luck with your exams because I'm recording this after the exams are over. So I'm curious to see whether this video will get any traction now that it's summer. Anyway, see you guys.